Peregrine is presenting our successful development of a passively cooled jet blast deflector for aircraft carriers. Peregrine has been in business for over 30 years, and we have focused on thermal control solutions, particularly high-temperature thermal control solutions. Here, Peregrine has applied our expertise in developing a passively cooled jet blast deflector. Peregrine is also active in thermal control solutions for satellites, hypersonics missile defense, aircraft, and then fusion and fission energy projects. Peregrine's challenge in producing this passively cooled jet blast deflector was to remove the need for cooling, which was provided by running seawater through channels within the JBD. The key objective is that the jet blast deflector is deployed as shown in the lower picture for launch. Once the vehicle launches, then the JBD is stowed back into horizontal position. Another vehicle rolls over the jet blasted surface and positions for launch. The rollover needs to happen within 10 seconds after launch of the previous vehicle, and the surface must be at or below 200 degrees Fahrenheit so that the next vehicle can roll over with its tires and not degrade those tires. The current actively cooled design using seawater taps into the seawater supply from the fire suppression system onboard the aircraft carrier. This takes away needed pressure potentially for emergency uses and offers another degree of risk with the current JBD design. Maintenance is also a key element of the current actively cooled design, and this is attributed solely to the use of seawater for cooling. Seawater is very corrosive to the aluminum-based structure that exists, and also to the coolant channels within the actively cooled JBD. Constant corrosion issues are present. The passive cooled JBD design by Peregrine eliminates the need for tens and tens of millions of dollars in maintenance due to the seawater corrosion annually. Peregrine's passively cooled JBD eliminates the need for seawater cooling, eliminates the burden of maintenance at sea. It eliminates the need for inspection and verification of the active cooling system to maintain an active status for the JBD while at sea. Noting that there are 4 JBDs per aircraft carrier, the probability of maintenance at sea is very high, and loss of one of the JBDs due to the maintenance requirements leads to operational readiness issues. Elimination of seawater cooling also eliminates the need to tap into the fire suppression system to provide the pressure necessary to provide cooling within the JBD. This allows the fire suppression system to be fully operational available for its intended need. The use of a passive cooled JBD versus an actively cooled JBD eliminates the need of tens and tens of millions of dollars of maintenance. The passively cooled JBD also has a projected weight of less than 50% of the actively cooled design. The key to the passively cooled JBD is the use of a turbulator design on the face of the JBD. Turbulators are grooves that elevate the contact of exhaust gas from the aircraft to the JBD surface. These grooves minimize the exposure of direct temperature to the JBD surface, leaving a fraction of the surface area exposed that can be quickly cooled between launches. The use of titanium is also employed for the JBD surface. Titanium takes a significant amount of heat to elevate its temperature versus the current aluminum design, preventing the rise of temperature of the JBD surface that assists in maintaining a low surface temperature. Titanium is also very corrosion resistant to seawater. The key features and advantages from the current baseline actively cooled design to the passively cooled design is simply the elimination of seawater as the cooling media. That translates into savings of tens of millions of dollars annually for maintenance and eliminates the risk of needing to tap into the fire suppression system onboard each aircraft carrier. It also eliminates the risk associated with having a JBD down for maintenance at sea and the potential need of that JBD. It also eliminates the risk of personnel on the flight deck performing maintenance. This passive design eliminates the need to expose personnel for maintenance duties. Peregrine has completed a 3-year effort of a Phase 2 SBIR demonstrating the success of a passively cooled design. Peregrine is currently seeking funding to deploy a working JBD, while we also seek out other uses of turbulators for non-JBD surfaces. Cooling is a major issue associated with turbine engines, along with other power sources, and overall cooling of electronics. JBD has the potential to assist in supporting thermal control of a wide variety of products. Currently, we seek assistance from the Navy transition this design into a fielded product. The market for JBDs are directly related to 11 aircraft carriers in the fleet. There are 4 JBDs per carrier, 44 JBDs in total. Each JBD is made up of 6 segments, so there is a total of 264 JBD segments that are 6 foot wide by 14 feet long, as shown in the previous illustrations. Peregrine is in a position to be able to deliver all 264 JBD segments and again seeks Navy support to allow us to do so with funding and installation support. Once successful here, there will be many other applications on Navy ships along with other vehicles to utilize this passive cooling approach. Peregrine looks to transition this technology to the Navy fielding the product. Peregrine has the ability to produce and to work with the Navy to transfer this important technology. Contact information for Peregrine is listed on this slide.